Namaste and a warm welcome to yet another lecture on mathematical foundations for machine learning. In the last class we were looking at the idea of field, which seemed to form the foundation for the concept of vector spaces, and in that context we said that okay, set of real numbers is a field. A field is nothing but a non-empty collection of elements which are closed under addition, multiplication, and has unique multiplicative inverse. That is what we said, and in the process we figured out that a set of real numbers is actually a field. We were also quite tempted to see if the set of integers was a field. Unfortunately, we figured out that the multiplicative inverses for integers were actually fractions and that were not in the set, and therefore set of integers failed to be a field. But we did not want to give up on the good point that we had about good features of or properties of integers, that we did not want to leave and then say look, we will completely keep away the integers. Instead we started probing a bit further, but by just modifying the addition and multiplication operation. What we did is we, instead of taking the entire set of integers, for example we took a set of integers modulo 5, that means you are looking at set of remainders that you would get when you divide by 5, and then we said that over this set we will define the addition and multiplication operations to be addition and multiplication operations modulo 5, and we figured out that set R5 is a field with operation modulo 5 addition and modulo 5 multiplication. Immediately we had another question. We said that look, we found that set of integers mod 5 is a field. Does that mean set of integers mod any other integer would be a field? So what we asked was, suppose I have n to be an integer and Rn is the set of all remainders that I would get when I divide by n. Is Rn a field for any n? This is the question that we had, and we want to figure out an answer for this, and that is what we are going to do now, and then we will go on constructing vectors out of the field and so on. That is the agenda for the class. So let us just look at a set of integers modulo any integer. So we took R5, set of integers mod 5. Now I am going to look at set of integers mod, let us say 6 and c. Let us just try it out. Set of integers mod 6 is basically what would you call, is basically an it is a field. Okay, so I am going to look at R6. This is nothing but set of integers modulo 6, set of integers mod 6, in which case I am going to define. So what is the set R6 now going to have? R6 is going to have number 0, 1, 2, 3, 4 and 5. So these are the set of remainders that we can get when we divide by 6. So I am going to define addition here as addition mod 6 and multiplication here as multiplication mod 6. I am going to do the same thing that I did with R5 and see if this guy R6 is going to be a field or not. So for that, what do? I basically construct a table like what we did last time. I am going to construct a table. So I am going to have numbers in each of these columns 0, 1, 2, 3, 4, and then I am going to have 5. So this is what we have: 0, 1, 2, 3, 4 and 5, and 0, 1, 2, 3, 4, and let me go down a bit and say okay, this is 5. I am going to do addition mod 6. I mean we already know like how do we add and then do a mod 6, that is pretty simple and straightforward. So I am going to have, this is 0, this is 1, this is 2, this is 3, 4 and 5. This is 1, 2, 3, 4, 5, and 1 plus 5 is 6, 6 mod 6 is 0. Then I am going to have 2 plus 1 mod 6 is 2, then we have 3, 4, 5, 6, and 6 is going to be again 0. So 6 mod 6 is going to be 0, and then I am going to have 1, then I am going to have 3, 4, 5, 0, 1, 2, 4, 5, 0, 1, 2, 3, and 5, 0, 1, 2, 3 and 4 is what we have. So basically what we do is we take every row element and then every column element you add them and then do a mod 6, find out the remainder that you would get when you do division by 6. So, this is what we have. Something interesting happens here, if when you add the elements of R6 with themselves and then do a mod 6, we see that the resultant, the sum is going to be an element from R6 itself. Therefore, we see that R6 is closed under addition. So, R6 is closed under addition, this is what we have. And now what we want to do is there is a and it is also closed under addition, and we see that additive inverse for every integer R6 in R6 exists. Additive inverse is basically you add two numbers from the set and the resultant must be 0 mod 6, that means you do addition mod 6 you get 0. So, for the case of 1 I have 5 to be the additive inverse, for 2 I have 4 to be the additive inverse, for 3 itself is the additive inverse, for 4 it is 2, and for 5 it is 1, and 0 of course 0 is the additive inverse. So, we have additive inverse to exist, then closure under addition is there. Therefore, there is a small hope for us to think that look, okay, R6 could be a field. Let us look at multiplication mod 6. So, now what I am going to do is I am going to do multiplication mod 6, in which case I will remove the 0, because anything multiplied with 0 is going to give you 0, and 0 does not even have a multiplicative inverse. So, I mean, so what we will do is we will just restrict number from 1 to 5. So, I am going to take this as 1, 2, 3, 4 and 5. I am going to take this as 1, 2, 3, 4 and 5, and I am going to do multiplication mod 6. What do I mean? Take every row element, multiply with every column element and do a multiplication mod 6. Something interesting happens here. Okay, let us see what is that. So, I have 1, 2, 3, 4 and 5. Then I have 2 into 1 is 2, 2 mod 6 is 2, 2 into 2 is 4, 4 mod 6 is 4, 2 into 3 is 6, 6 mod 6 is 0, 2 into 4 is 8, 8 mod 6 is 2, 2 into 5 is 10, 10 mod 6 is 4. Similarly, you take 3, you get 3, 3 into 2 is 6, 6 mod 6 is 0, 3 into 3 is 9, 3 into 4 is 12 mod 6 is 0, 3 into 5 is 15, which is 3. Then I have 4, 4 into 2 is 8, 8 mod 6 is 2, 4 into 3 is 12, 12 mod 6 is 0, 4 into 4 is 16, mod 6 is 4, 4 into 5 20, mod 6 which is 2. Then we have 5, 5 mod 6, 10 mod 6 is basically 4, 15 mod 6 is 3, 20 mod 6 is 2 and 25 mod 6 is 1. Now, there is something interesting that happens here. No, in the case of mod 5, when we looked at the table for mod 5, we did not find, when we did multiplication, we never found anything which is 0 in the table. We just took numbers from 1 to 4 in the column and in the row side, and then when we multiplied and did a mod 5, we ended up getting numbers from 1, 2, 3, 4. But in this case, when we do this mod 6, we seem to have gotten into some mess. What is that mess? You end up getting 0, which was not even something which you are considering, and except for two numbers, except for two rows, which basically corresponds to let us say this one and let us say this one, all other rows do not have a 1. Oh, that simply means there is something wrong here. There is nothing wrong, but just that you do not get, when you multiply two numbers and then for example you take the number 2, look at the row corresponding to 2, in none of the column you get a 1, look at the row corresponding 3, in none of the columns you get a 1, and then look at the number 4 and in none of the columns you get a 1, which means you cannot find another integer in R6 such that when it multiplies 2, 3 or 4, I mean correspondingly, like you can't find one integer which when you multiply with 2 and then do a mod 6 you get a 1, you cannot find another integer multiply it with 3 and then mod 6 you get a 1, and you cannot find a third integer 4 which when multiplied with 4 and do a mod 6 you are going to get a 1, which means these guys 2, 3 and 4 do not have multiplicative inverse. And the very core property of a field is that every non-zero entity in the set must have a multiplicative inverse, and here in R6 we see that there are 3 of those numbers which are there in R6, 3 of those elements which we have in R6 do not have multiplicative inverse. That means we are going to say that look, R6 is not a field. Why is it not a field? R6 is not a field because it does not have multiplicative inverses for some of the element, multiplicative inverses for some of the elements. Oh, looks like we are in deeper trouble now, because we said R5 was a field and you just take the number next number to 5, which is 6, you say R6 is not a field. That means, are we heading to a point where we are going to say that, look, the set of integers modulo any odd number is going to be a field? Maybe you can check as a small exercise, you can check R3, R7 and so on, and probably you can even try R9 and see whether each of these is going to be a field. Looks like there is some problem here. So, these are not, I mean R6 is not a field. Therefore, what is the condition for a set of elements modulo n? What should be the condition on n for Rn to be a field? Rn in the sense here the set of integers modulo n, that is what I am looking at. What is it that what is the condition on n such that it is a field? Now, let us examine this R6 a bit closer. Why did we not have multiplicative inverse for 2 mod 6, 3 mod 6 and 4 mod 6? It simply means that I mean if you look at the greatest common divisor of 2 and 6, the GCD is 2, greatest common divisor of 3 and 6 it is 3, and greatest common divisor of 4 and 6 if you take, that is going to be 2. And in the case of 5, you take all those integers which are less than 5, the greatest common integer, the greatest common divisor between that integer which is smaller than 5 and 5 is always 1. That means whenever the n that you are looking at, which is the mod n that you are trying to do, that n we are looking at, whenever that n and the other integers are relatively prime to each other, you seem to get a field, and whenever they are not relatively prime implies the GCD being 1, whenever that does not happen, you see that the set is not a field. So, what we are going to do is we are going to say that, okay, let us not complicate further. What we are going to say is Rp where p is a prime integer or a prime number is always a field, where p is a prime and the set of, okay, let me put that in bracket, the set of integers modulo p, the set of integers mod p is always a field. Now, that brings us to a question. So, is R2 a field? I want to look at R2, that means I am going to look at set of integers mod 2. So, what are the elements that we are going to have in R2? R2 we are going to have just 2 numbers 0 and 1. This is basically set of integers mod 2. So, I want to check if this is a field. So, let me do the addition modulo 2. So, I am going to have 0 1 and 0 1. So, I am going to have 0 plus 0 is going to be 0, 0 plus 1 is 1, 1 plus 0 is 1 and 1 plus 1 is 2, 2 mod 2 is going to be 0. And let me also look at the multiplication here. I am going to look at this. There is only one number that we have, non-zero number, which is basically 1. So, I am going to do this. So, I am going to have 1 into 1 mod 2 is 1. Suppose you want to take 0 also, 0 does not have multiplicative inverse, no problem, we can multiply. So, this is going to be 0, everything is going to be 0. So, now what we see is you have additive inverse for the number 1 in modulo 2 field or modulo 2 set in this set. If you add 1 and do a mod 2, you are going to get 0, that means 1 is the additive inverse of itself, and 1 is also the multiplicative inverse of itself. If you multiply 1 with a 1 and do a mod 2 you end up getting 1. So, that is a multiplicative inverse of itself. So, R2 is a field just with these two elements. So, I am going to say R2, which is basically set of integers modulo 2 is a field. In fact, a very interesting thing that to note is this is something which you would have observed. What is that? This modulo 2 is basically, if you look at this, when the inputs are different the output is 1, when the inputs are same like here when you have the inputs to be the same, the output is going to be, in this case the output is going to be 0. This is what you would have studied in your binary or your logic gates as your XOR gate. So, you have modulo 2 addition, which is basically the XOR gate or the XOR operation, and we would see this where we have this when you have 0 and you multiply with every other number you are going to get 0, and only with 1 when both the inputs are 1 you are going to get the output to be 1, and modulo 2 addition multiplication is corresponding to your AND operation. In fact, what is more interesting is like whenever somebody asks you like in binary why would you have just zeros and ones, typically people will say look it is going to represent high and low, high voltage and low voltage like levels, basically 1 is high voltage level and 0 is the low voltage, let us say 5 volts and 0 volts and so on. And many times you find them not giving an answer as to why it should only be 1 and 0. If it is going to be just high and low you could as well have root 3 for high and root 2 for low, or you could probably have pi for high and then probably 1.2 for low. You could have all that, but you do not. The reason being you are looking at this, the only reason why your binary, whatever binary system that you do which you encode in terms of ones and zeros is because these are the remainders that you would get when you divide by 2, and this is something which many people do not really consider. They always have they always equate it in terms of the voltage levels and then say look high means 1 and low means 0. No, it is not. It is basically when you do a modulo 2 addition or when you do a modulo 2 operation you are just going to get two numbers which are 0 and 1, and that is why your binary is a string of zeros and ones. Okay. And in fact you would see that when you try to convert a decimal to a binary you are going to write the remainders, right. You are going to write you are going to successfully divide by 2 and then you are going to write the remainders in the reverse order, and that is exactly what your binary is, which will only have zeros and ones. This is precisely why it is so, right. So, what we are going to say is we had a problem with the set of integers which were not field. Now what we did, we overcame that problem by just saying look I may not have set of all integers to be a field, but instead I can have set of integers modulo a prime number to be a field, which means we will have only a fewer elements there and then your operations are defined and then you see that it is closed under addition and scalar multiplication, and whenever the modulus whenever the mod the n that you are going to take is going to be a prime number you are going to have multiplicative inverse also to be defined, and that is exactly why you see that it is a field, right. So, we found that set of real numbers is a field, set of integers modulo prime is a field. So, what we will typically be doing is in this case we will define all our for future classes whatever that we are going to do as a part of linear algebra we are going to look at real field. Okay. So, that is what we are going to do. Now, where do we go from here? Okay, fine, I have a field. So, what, where do I go now? So, the next question that we are going to answer is using the field can we do something. So, what we are going to do is we are going to define something here, we are going to define the idea of vector space. I will make the mathematical definition now and probably give an example and more intuition about this after doing this definition. So, we are going to get into the idea of vector space V, where we are going to construct vectors. We are going to construct a new mathematical element called vector by making copies of this field. Suppose you make just 2 copies of the field and then that means for example you take the field to be the set of real numbers, the real field you take. Now what I do is I try to make 2 copies of the field. One copy I call it as my x axis, the other copy I call it as my y axis. Now what I am going to do is I am going to pick one number from the the real line corresponding to x axis and one number from the real line corresponding to y axis, and I am going to look at the Cartesian product of that, and I am going to call that as a 2 component vector. Now therefore, you can make any n copies of the field and then you end up getting r to the n, right. So I am going to have n component vectors. I am going to have a set which contains where every element you call every element to be the vector, and each vector is going to be I mean it is going to have n components, right. So that is what we are going to say. So I am going to define a new mathematical structure called vector space, which is denoted as V. We will come back to what this vector space could mean and what are all the other things that we will look at after writing this formal definition, right. So what we are going to do is we are going to look at this vector space V. So what does it mean? So where does the definition start? So we are going to start with, let us say, let F be any field, be any field. Now what we are going to do is we are going to say let this V be a non-empty collection, of some objects, and these objects are what we are going to call as vectors. That means every element of the vector space is going to be called as a vector. So non-empty collection of objects called the vectors. So now what we are going to do is we are going to define a vector space. We are going to say that look, V is a vector space over F, V is a vector space over F if there are certain rules that exist. If the rules for adding two vectors and scalar multiplication exists such that V, whatever that set V we have, we want to say such that V is closed under vector addition and scalar multiplication. Now what do we mean by this? How are we going to do this mathematically? Scalar multiplication. So how are we going to define this mathematically? So let us do this mathematically. We have the following what we call rules. So that is what we are going to write now. So the first one we are going to say for u comma v, for u comma v in this big V, u plus v is an element of V. Then for say alpha the scalar in the field and u an element of V, u an element of this big V, alpha u is also an element of V. That means the first case is where when you add two vectors, the resultant vector is also going to be an element of V, and when you take a scalar, when you take a field element and multiply this vector by the field element, then the resultant you are going to get is a vector which is also an element of this V. So this is what we call them as closure under vector addition and closure under scalar multiplication, and we also say that there are some more properties which must hold good, and the following properties hold good. Following properties hold. So, what are the properties? The first one we are going to say, look, I want to look at number 1, which is basically the idea of commutativity. Now, what does that mean? If you have for all u and v, for all u comma v elements of this v, u plus v, the order in which you add the vectors does not matter. The second property that we are going to have is basically this. We are going to have the associativity. So, suppose you have these vectors u, v, w in f in v, then we have, if you take 2 of them and then add with the third, it is the same as adding the other way around. It is the same as the grouping that you do does not matter as far as addition is concerned. So, if you take u plus v and then get the resultant, add with w, the result is going to be the same as taking v plus u, getting the resultant and adding with u. And suppose you have scalars. So, for scalars alpha and beta, let us say element of the field, and let us say u an element of the vector space of the set V, I am going to have alpha beta into u is the same as alpha into beta u. That means, you can multiply the scalars and then you can scale a vector, or what you do is you scale a vector and then multiply and then scale the resultant again, the resultant that is what you call as your associativity. The third property that we are going to look at is distributivity. Now, what does that mean? You want to see how are the operations going to be working when you have the scalar multiplication and vector addition together. So, I am going to say for alpha in field and u comma v in v, we have alpha into u plus v. That means, it is the same as, that means you take the resultant of u and v, that means you add the two vectors, whatever resultant you get you scale that by alpha. It is the same as scaling individual vectors and then adding them. It is the same as scaling the individual vectors and adding them. The other thing is, you can also have this property which says, look, suppose you have two scalars, let us say alpha comma beta from the field and u element of v, then if you have two scalars and let us say alpha plus beta into u is the same as alpha u plus beta u, right. This is there, and in addition we also have a couple of other properties. Let us see what they are. So, we are going to have this, the fourth one, which we say the additive identity element, additive identity element. That means, you have the 0 vector which is an element of V such that 0 plus the u vector, I am taking this as 0 vector, 0 plus u vector is the same as u vector for all u vector in V. We also have additive inverse, for every vector. What does that mean? We have that for every u in V we have there exists a minus V or minus U in V such that U plus minus U is equal to the 0 vector. Now remember, all these things are vectors, and the last one is basically the multiplicative identity. So, I am going to have this, the last one is basically my multiplicative identity. So, what does this mean? You have the scalar 1 identity. So, we have 1 into U is equal to the U vector. Here you see 1 is basically a scalar, this is a scalar, this guy is a scalar, this guy is a vector, and the resultant is a vector for all U in this V. If all these hold good, then we say that V is a vector space. If all these properties hold good, that means it is closed under vector addition, scalar multiplication, and existence of this additive identity vector, that means the 0 vector is there, then you say that the set is going to be a vector space. So, come on prof, this next question that I can ask is like, come on prof, you have been telling all vector space and elements and all. First of all, tell us how do we even construct a vector? That is a question that we need to answer, which we have not even looked at. So, in the simple term, what we will do is we will just look at this. So, how are we going to construct a vector? For example, I want to construct a 2 component vector, construct a 2 component vector. From the field or over the field, say over the field F. Now, what are we going to do? Here we are going to take a simple example. Let the field be the field of real numbers, let F be equal to R. Now, I am going to make 2 copies of R, as I said before, I am going to make 2 copies of R, and then what I am going to do is I am going to construct a vector. Now, that is exactly where I come to. So, I am going to have 2 copies of R, I am going to define a vector U, which is nothing but U1 U2, which is basically an ordered pair, that is what you would have done before, right, x comma y coordinate, and you will say no, in xy plane x comma y is basically a point where x is the first axis component and y is the second axis component. That is exactly what I am going to do. So, I am going to do the same thing here. I am going to take 2 copies of R, and then I am going to get this U1 as an element from the first copy of R or 1 copy of the R, and then U2 as the next element, which is from the next copy of R that I make. Therefore, I say U is a 2 component vector, 2 component real vector. That means the 2 component real vector, that means the elements are all real numbers, right. Now, I can make why only 2 copies, let us make n copies of R, let us make n copies of R. So, what I am going to have is I am going to have this vector U, which is going to be given by U1, U2, etc. Un. That means every value, every component basically comes from 1 copy of R. So, each component comes from 1 copy of R. So, you are going to have n components. So, we say that U is basically an n component vector. So, this implies when you have a 2 component vector, we say U is an element of R2. How do we get this R2? This is the Cartesian product, you have R cross R. So, I am going to call this as R2. In this case, I am going to call this as n component vector. So, R cross etc. R n times. So, I am going to call this as an Rn. So, I am going to say U is an element of Rn. U is an element of Rn. So, U is an Rn component real vector, that is what we have. Okay. Now, we know that there are certain properties we know how to construct a new mathematical structure, and the one thing that we have not seen is like how do we do this vector addition and scalar multiplication in this case. I will do it right away, and then we will take some examples for vector spaces. So how do we carry out vector addition? So that is a good question. So we have how do we carry out vector addition, how do we do vector addition. So suppose I have u to be an element u comma v to be an element of R2, that means the vector space V is defined over R, V is defined over the field R. So what does that mean? If I take the vector u, I am going to have two components u1 u2, both of them are going to be real numbers. So I am going to say u1 comma u2 both are real numbers. Similarly, I am going to have this vector v which is going to be v1 v2, and v1 comma v2 are both real numbers. Now what I am going to do is I am going to define vector addition as u plus v, which is nothing but u1 u2 plus v1 v2. Now if you look at this, I am going to write this as component wise addition, that means u1 plus v1, u2 plus v2. Now there are a few things that you have to note here. What is that? When I use this here, this plus that I have correspond, this plus that I have, they correspond to vector addition. Whereas this plus that I use here, these two guys, these are basically the addition as defined over the field, as addition as defined in the field. Why? Because u1 and v1 are field elements, therefore if I want to add those two guys, the addition must follow the addition that is defined in the field. So addition as defined in the field R. Okay. Now what we are going to do is let us look at scalar multiplication. So scalar multiplication is basically this. Suppose I have an let alpha be a real scalar, that means I am going to take alpha to be from the real field, and my vector u is basically a two component vector that I have u1 u2, and u1 u2 are real numbers. That means I am going to define my vector space over R, the real field. I am going to define alpha into u, which is nothing but alpha into u1 u2. This is nothing but alpha into u1 alpha into u2. The same thing if you see, this is going to be, if you look at here, this and this corresponds to your scaling operation. This multiplication is basically scalar multiplying with a vector. So this is basically called as the scalar multiplication of vector, scalar multiplication of a vector. Whereas this that you have here, here and this, these are basically multiplication as defined in the field, as defined in the field. In this case it is going to be R. That means you know how to multiply two real numbers, and that is exactly what this is. This in some sense is also like your operator overloading that you do in programming, where the same operator is going to be conveying different meaning at different points in time. When you do this here, this guy is going to be scalar multiplication of a vector, here it is just going to be multiplication of two real numbers. In this case if you see this and this corresponds to vector addition, whereas this corresponds to the addition of two real numbers or two field elements, where the addition is as defined in the field arithmetic or as defined by the field arithmetic, right. So that is what it is. Okay, good. So it's a good time to conclude this lecture, but we will conclude it with a question for which we will try to answer it in the next So, the question is, give us some examples for vector spaces, examples for vector spaces. And a very relevant question that we can ask is, look, the course is titled Mathematics for Machine Learning or Mathematical Foundations for Machine Learning. So, what does this idea of vector space mean in machine learning? What is the machine learning context of these vector spaces? How are we going to do this? The answers for which we will try to get it in the next lecture. Namaste.